Classical learning theory tells us that simple models work best. Complicated models are less likely to generalize new data. Deep learning is considered mysterious because it has tons of parameters. This lets it memorize arbitrarily complicated solutions, but in practice, large neural networks tend to find solutions that generalize well. Why? One explanation is called the volume hypothesis. Even though a big network can do lots of things, maybe the volume of the simple solution is much higher than the complicated solutions. To explain in more detail, here's a cartoon of the loss landscape of some data. We can find a variety of parameters that minimize loss on the dataset. These are called minima. The volume hypothesis argues that some minima are much larger than others, so we're more likely to find them using gradient descent. Why are large minima good? Well, there's an idea called the flat minima hypothesis, which argues that a minima that is flat in parameter space, meaning you can adjust the weights without having the loss values go up too fast, will generalize better. Meanwhile, minima which are sensitive to parameters generalize poorly. To test these ideas, we can do experiments. We take some data set, we fit a model, then we generate some bad models by adding poisoned data points to fit through. We measure the volumes of these models to see whether or not they agree with our explanation. What exactly do we mean by volume? Imagine we have a model with two parameters A1, A2. Training on a dataset leads to values that minimize the loss. If we change A1 and A2 by some perturbation, that loss will increase. We move along this perturbation until it exceeds some sort of loss threshold. Repeating this with multiple directions gives us an estimate of a basin volume where the loss remains below some threshold. Volume is thus a measure of flatness that's directly related to the probability of getting this minima from random parameters. Measuring volumes on our experiment shows the model trained on the correct dataset has way higher volume than the models trained on the incorrect data. The amount of incorrect data they're trained on is inversely related to their test accuracy, and thus we find that the volume and flat minima hypotheses are a good explanation for why we don't get these bad solutions in practice. This paints a very nice picture of deep learning. It's easy to find large minima thanks to the volume hypothesis, and large minima generalize well thanks to the flat minima hypothesis. So deep learning is easy. Except, no. Deep learning only really works well with large datasets, so either the volume hypothesis or the flat minima hypothesis can't work well in small datasets. Which is it? Note that volume and other flatness measures depend on the dataset they're being measured on, so it's plausible that either of these could be wrong. In order to test this, we devise our own experiments. We can form subsets of MNIST, we'll call them D1, D2, D3, where D2 is D1 but has more data. We train models on these different datasets and evaluate their volumes. We find in the small dataset D1, the model trained on that dataset M1 is the largest in volume. However, M1 also has the worst test accuracy of all the models because it was trained on the least amount of data. Meanwhile, M3, trained on the largest amount of data, has the smallest volume despite generalizing best. These results don't seem to depend very much on the threshold value that we choose for our basin, which leads us to be fairly confident about them. From these results, we see the volume hypothesis seems to work well in small datasets, but the flat minima hypothesis doesn't work well. Does this trend only hold in small datasets? Our experiments suggest that for MNIST, this trend continues. We plot how model volume changes from smaller to larger datasets. M1 is initially very big, but when we add data, this minima decreases in size because it increases in loss. Eventually it has zero volume under our chosen threshold. M2 has less volume in the small dataset, but in the D2 dataset it has the largest volume. It shrinks eventually, and M3 is now the largest, which explains why we find it. The volume hypothesis seems great for predicting the models that we observe. On the other hand, the flat minima hypothesis doesn't work so well. Does this mean flat minima are bad? Not necessarily. Our experiments suggest the loss landscape is full of sharp minima, which are bad, but there are some rare gems. Deep learning sidesteps these bad minima by only going for the flat minima, which seem to do relatively well, not amazing, but not very bad either. We also did a couple other experiments in our paper, such as problems like CIFAR-10, recreating past experiments with batch sizes, sharpness-aware minimization, grokking. If you're interested, please consider reading the paper. Our conclusion from all of our results is that flatness isn't a very good guarantee of generalization. The large models that we're using nowadays that rely on huge amounts of data seem to actually be sharp minima. Given that we haven't found particularly good flat minima, it might be time to focus our attention on ideas aside from sharpness. As for what they are, that's going to be left for future researchers to figure out.